my finger is now the pen. I don't want that to be the pen. Buffers are not, I wish it was simple, but buffers are complex. Okay, so I wish we were ending on something that was super easy, but I'm not going to lie to you. I'm not going to sugarcoat it. Buffers are quite a concept. And so with that said, I can promise you, you can take this to the bank. There will be a buffer problem on exam 4. I tell my students that every year, trying to give you a heads up. They are a 3-part problem, okay? Buffer problem will be on exam 4. Write that down somewhere. Write it down on whatever you're going to study. Remind yourself. It's a 3-part problem. We will look at what happens to a buffer when we add an acid. We will look at what happens to pH of a buffer system when we add a base. And you will have to calculate the pH of a buffer system, okay? So just letting you know, if you can do that, that's a solid 10 to 15 or more points on the exam already. We ended with this problem last time, and I'm going to have this on the review for exam 4. And if we have time today at the end, I'll come back and work this. I just don't want to shortchange us with what we got to do. So maybe come back and work this problem, but if not, we'll do it on a review. So I'm going to go ahead and jump in with buffers. So let's define what a buffer is. It is a combination of substances in a solution that act together to resist changes in pH. Okay, buffers want to maintain a pH. They want to stabilize a pH. They don't want pH to change. And this is important for many reasons. It's crucial to maintain proper pH in biological systems. The main one we're going to talk about today is our blood. And I don't care what area of health science you're going into, blood is important for all of those things, even communication science disorders. And we use buffer systems also to maintain pH in laboratory solutions. And, you know, hospitals have laboratories, clinics have laboratories, research labs, of course. And so I can't tell you how many times I stood at how many hours of my life. Have you ever wondered this? Like, how many hours have you sat at a traffic light? How many hours have you spent in a grocery store? How many hours of my life did I spend at a pH meter? Okay, a lot. A buffer system, here's what it is. It's usually a weak acid, and it's conjugate. I'm going to abbreviate conjugate base. So we talked about weak acids and conjugate bases Tuesday. I'm trying to remember what day it is. And I want you to look at these reactions down here. We've got a generalized one on top, and then we've got one with acetic acid on the bottom. I want you to label the weak acid and the conjugate base. Which one is the weak acid? Which one's the conjugate base? Notice they are equilibrium systems because you have the double arrow. We got equilibrium here. So take a second and label that. Okay. Weak acid and conjugate base. Notice I did not say strong acid. You cannot have a buffer system with a strong acid. You have to have something that has an equilibrium, okay? So if you're looking at the first one, what is the weak acid here? You can type it in the chat or say it. Abby says HA, and she is correct. Okay, this is your weak acid. What is the conjugate base? Anyone? A minus. All right. Now, if we're applying it to a real acid and conjugate base, we have acetic acid and water. And by the very name, we should know acetic acid is our weak acid. And don't just think the weak acid is what I write first. I know that happens to be the case here. The weak acid could be the second reactant. It just happens to be the first in both of these. But don't think, oh, it's always the one written first. The conjugate base is the form of acetic acid minus a hydrogen, and that is the acetate anion in this case. All right. You have to have these components to have a buffer system. All right. So we're going to draw a diagram that, because I'm going to ask you on the exam in some form or fashion, whether it be a multiple choice question or a short answer or whatever, about buffers. There will definitely be buffer pros. I want you to know how buffers work, okay? And so this diagram will help you answer any of those questions. I want you to know how a buffer would respond if we add some sort of a strong acid or a strong base to it, how it neutralizes those things to maintain pH. So let's say we have our weak acid. I'm just going to use HA and A minus for this diagram. If we have HA, and I'm not going to write water in right now. I'm just going to write the weak acid and the conjugate base. And let's say we have, the equilibrium, and on this side, the product side, we always have the conjugate base. All right, so what happens if this is working to maintain pH? What do we know about acids and what do we know about bases? Well, acids, what do they do to pH? Acids, they donate a hydrogen ion to solution. They create these. They increase the concentration of H plus in any solution. And what does H plus do to pH? If we increase the amount of H plus in solution, what happens to pH? Should I draw an up or down arrow? Remember, I wrote this up here when we ended. I said, put a star by this. This is an important relationship. We said if we increase H plus, this over here, pH drops. It's the low pHs that are more acidic. So if we are adding an acid to a solution, we're dropping pH because we're increasing the concentration of H plus. So now, if we're looking at the conjugate base or the weak acid in our buffer system, this is our buffer down here. We want to, the way a buffer works is it kind of snatches up any component from solution, meaning it binds with it, and that's how it neutralizes it. The moment H plus is bonded to something, some chemical, whatever, now it's part of a molecule and it's neutralized. Okay, it cannot decrease the pH. So we want to bind it. We want to find something and snatch it up out of solution. So look at our weak acid, look at our conjugate base. Which one do you think would do a better job of snatching up any loose hydrogen ions in solution? Abby says the base, Jenna says the conjugate base. That's correct. You can think about it from a charge standpoint. We've got a negative charge on the conjugate base. Negative charges are attracted to things that are positively charged. Hydrogen ions are positively charged. So what happens if we have some free-floating hydrogen ion, and where did that come from? That came from the addition of a strong acid. Let's say we add some HCl. This is a strong, I missed an end. If you comment on my spelling skills in my eval, I will not be surprised. All right, wow, I'm still wrong. Okay, there we go. Strong acid to solution. We know this dissociates into H plus and Cl minus, right? And so this is where this H plus comes from. Whatever acid we added was created from that acid. Now, this guy is free floating and this is conjugate base is going to come in and snatch it up. What do we make when we do that? We make more of our weak acid. All right. And now this has no power to change pH, okay? It's not a weak acid that changes pH. It's the free-floating hydrogen ion. And if we are binding up that hydrogen ion, we're creating more weak acid. Weak acid does not change pH. It's only when it disassociates that it changes pH. So we just prevented the pH from dropping. So that's one way a buffer works when we add any kind of an acid or strong acid. Okay, what happens if we add a base? An example of a base is OH minus. We know this is a strong base. And what happens if we raise the concentrate? Bases contribute this to solution. And what happens if we increase the concentration of hydroxide in our buffer setup? Remember, go back up to this relationship. I actually didn't write it in. Well, I did write it on this side. We said if we increase, I did. Increase the concentration of OH minus, pH would go up. And the buffer doesn't want that to happen because we said a buffer is resisting changes in pH. So if we're doing this, which component of our buffer system do you think could neutralize OH minus? How do we neutralize OH minus? What can we do to it to turn it into something else that has no power to change pH? HA, turn it into water. Bingo. Bingo. If this weak acid would disassociate and snatch up this OH minus, guess what it's going to create? It's going to create H2O. And in the process, it's going to create more A minus. Because HA is going to turn into, well, H plus and A minus. The H plus, I should actually write this slightly different. Sorry, I keep erasing. The H plus is going to go this way with the OH minus, and then what's left over is we're going to create A minus, more the conjugate base. Okay, and we just neutralized the OH minus by turning it into water. This is powerless to change pH. Okay, so this diagram right here, I think I have a simplified version on the next page. This is a diagram that I want you to be able to kind of sketch out to understand and walk yourself through. If we add an acid or if we add a base, well, what happens? How does the buffer respond? If we add acid, the equilibrium is going to shift towards reactants. We're going to make more of our reactants. This is if we add acid. If we add base, it is going to shift towards products. We're going to make more of the conjugate base. Questions on how this works? Do I need to walk through anything again? Does that make sense? So that is how we neutralize things to prevent changes of pH. Here's the diagram on the next page. Okay. This shows you if we're adding a base, what happens? This shows you if we add an acid, what happens? So now let's just do a walkthrough with these questions down here. Now, let's say we just have water, no buffer system. Let's say we just have water. This is kind of just a review to check your understanding real quick. If we dump a bunch of sodium hydroxide in water, what would happen to the pH? Remember, you don't have a buffer here. You just have water. Kathleen says pH would increase, and she's correct. We could even write out the equation, NaOH plus water. Well, this is the base, and what do bases do? This is going to be the acid in this case. This is a strong base, so I'm not actually even going to write an equilibrium here. Strong base is going to drive it all to products. We're going to have OH minus. This is going to disassociate. And that OH minus is going to grab a hydrogen from the acid and we'll make more water. But when we take a hydrogen off water, we're going to end up with more OH minus. It feels very redundant. And then we'll still have that sodium ion floating around. And this guy right here, the presence of that in solution will increase pH. Okay, so pH will increase. There's nothing there to neutralize it. Now, what happens to pH if we add NaOH to the above reaction at equilibrium? Meaning the above reaction is right up here, the acetic acid reaction. Look at acetic acid here. Which component of acetic acid, or the acetic acid reaction or equilibrium, would neutralize sodium hydroxide? Dennis is the weak acid. And some of you might be confused. You might be like, well, would H3O plus do it? Would the acetic acid do it? It depends which one's the stronger acid. And here, acetic acid is the stronger weak acid, okay? It's this component and this component that actually constitute the buffer. So acetic acid, okay, CH3O, COOH, here's our acidic hydrogen. Remember, it's the ones connected to oxygen that are acidic. And NaOH. So the OH portion of this base would grab this hydrogen, and an acetic acid would gladly donate it to neutralize the hydroxide. And we're going to make water. Actually, we have a strong base here, so we should not write an equilibrium. We should write it all this way. We're going to make water, and we would also make, we have the sodium ions and CH3COO minus. Now, if you wrote it like this, sodium acetate, as a neutral compound, I would not count you wrong. You can write them as separated ions still, or just as the compound, either way. But essentially, what we just write is that acetic acid, to answer the question, would neutralize the OH minus, the base. pH would not change. We could write that in here. Now, I want to make a point, because you will see when we work buffer problems and we calculate what's going to happen to pH when we add a base or when we add acid, you'll see that pH actually does fluctuate a teeny tiny amount, like 0.02 or 0.05 change. But it's not a drastic change, okay? So we say it wouldn't change. It might fluctuate a little bit, like it might go up by 0.1. But that's totally tolerable in biological systems, okay? All right, now let's look at it from the flip side. If we add HCl to this acetic acid equilibrium reaction up here, what happens to pH? Which component is going to work to neutralize that HCl? Jenna says the conjugate base, which is the acetate anion. So what we would have is CH3COO would swoop in, and it would, we have HCl, which is going to disassociate to H plus and Cl minus. So it would grab this H plus, and it is going to make acetic acid. And then we'll just have Cl minus left over. So we say the acetate anion, which is the conjugate base, would, the word here is neutralize the H plus. And again, pH will not change. Okay. Okay, so we've looked at this diagram, we've walked through examples, different style questions. Now this is where the math enters into buffers, okay? So put your math hats on, turn your math brains on. This is an equation we're going to use. This will be on your exam 4 resources page, but you will need access to this Henderson-Hasselbalch equation. I'm not going to yell it, but if I could yell, I would. This is only for buffers, okay? If I ask you to calculate pH and I say, but I don't tell you have a buffer, don't use Henderson-Hasselbalch. Okay, we have a different equation. This is chapter 10 is pretty layered because we have all these different equations. Think of all the equations we have for pH. We have pH equals the negative log of H plus. Okay, we have 14 equals pH plus POH. We have all these different equations where pH is in the equation, and you can get confused. Which equation do I need? All right, this one you only need it if you know in the problem I tell you it's a buffer. Okay, only for buffers. So say we have some weak acid here. We know we can write an equilibrium expression for that acid. Okay, it's actually shown right here. Ka equals products over reactants. We actually we walked through how to do that on Tuesday. I'm not going to sit here and derive this equation for you, but the Henderson-Hasselbalch equation is just a fancy derivation of this Ka expression, okay? That's where it comes from. And here's what it is. Basically, if we have any buffer, and look, here's our buffer components. Here's the conjugate base, the concentration of it, and the concentration of the weak acid. If we know those things, we can take the log of them. We can add that to pKa, and I'll explain what pKa is in a minute. You're like, what's pKa? And we can calculate the pH of that buffer solution. Another thing that gets confusing, and I admit this is confusing about this equation, is that there's a plus sign here. You're so used to doing negative log over here. Okay, you're so used to taking the negative log of H plus. And you do to calculate pH for any other solution, for any solution of an acid or a base. But the moment you have a buffer, you need to use this equation. Now, you shouldn't have to do a whole lot of work to memorize this. You should have it in your notes. So don't stress out about that. It'll be available to you. Just make sure when you're actually writing it in, you don't accidentally put a minus sign there. All right, so Henderson-Hasselbalch equation says that pH of a buffer solution equals pKa plus the log of the concentration of the conjugate base on top, weak acid on bottom. Another way people mess this up is they'll flip these. They'll be like, oh, which way was it? They'll get these flipped. Again, you should have this in your notes. You'll have it on the resource pages. There's no reason you should accidentally flip that, okay? But just pay attention. What is pKa? Well, we know what Ka is. We know what Ka is. If I give you, remember that table of Ka values from Tuesday? All the weak acids, and we looked on there and we said which one's the weakest weak acid, which one's the strongest weak acid. If you have a table of Ka values, P stands for the negative log of something. So all we've done is we've taken that Ka value and we take the negative log of it. Ka is a numerical value. It's usually a number with a really small exponent, like 10 to the minus 5 or 10 to the minus 4 or 10 to the minus 13. You're just going to plug that Ka value in, take the negative log of it. That is equal to pKa, right? And that's what we plug into Henderson-Hasselbalch equation. Okay, so now that your head's like swirling, your mind is rolling, we're going to talk about good qualities of a good buffer, and then we're going to put pKa and pH, Henderson-Hasselbalch, into practice. We're going to look at how to calculate pH. Qualities of a good buffer. What makes a good buffer? Well, first off, this one's obvious, but we have to have a weak acid plus the conjugate base, okay? This is just a reminder. You cannot have a good buffer with a strong acid or a strong base. Weak acid and its conjugate base. The second quality of a good buffer is that you have, sorry, I want to make sure I get these in order. Roughly equal, so it contains approximately equal amounts of the weak acid and conjugate base. Okay, now why is this important? Think about this. You want equal amounts of these things because you don't know what's going to be added to the buffer solution. A buffer never knows what it's going to have to neutralize, okay? So it's kind of like if anybody's ever watched, Lord, I don't watch sports very much, but if you know anything about football, you need to have equal number of people on the defensive team as you do on the offensive team, okay? Because both sides have to go out into the field at different times and play. And it's kind of like you never know when the defense is going to be called out or when the offense is going to be called out. Same idea here. If this is the offensive team and this is the defensive team, you want equal players. You don't know which way you're going to have to neutralize something. So if I had 100 molecules of my weak acid, but I only had 10 of my conjugate base, I'm not going to be able to neutralize the addition of an acid very well. Okay, so you want equal amounts. You want on both sides. All right. There's my one sports analogy for the day. Number 3, what this means is that the buffer works best if the solution that it's in, sorry, hold on, I have to move something. If the solution of the buffer is being kept where the pH is approximately equal to pKa, okay? you're like, what, I don't even know what you just said. What does this mean? If the pH of our buffer solution is approximately equal to the pKa of the weak acid, remember any weak acid has a Ka value assigned to it. So we can also calculate the negative log of any Ka. We can get pKa for any acid. I want to look at this equation right here. Take your calculator, grab your calculator, and I want you to do the log. Type in the log of 10 divided by 10. Log of 10 divided by 10. Because if we're saying, or you could do 100 divided by 100, right? That's what we said over here. We want 100 of these and 100 of these, or just the same number. Just do the same number on top, same number on bottom. You could do the log of 10 divided by 10, 100 divided by 100. What do you get? When you have the same number on top, you get 0. Okay? So this whole term goes to 0, and what's left? We said it's the strongest when the numbers of weak acid and conjugate base are the same. And when that's the case, which is the quality of a good buffer, you have roughly the pH equals the pKa, because this whole term goes to 0. So what that means, your pH is going to be whatever your pKa is. And if that's the case, then that is a quality of a great buffer, okay? So we're actually going to work a practice problem on that in a second to help us figure out how to apply that. Lastly, you want the molar amounts of the weak acid, which is HA/A- conjugate base, to be in excess. Okay, roughly 10x, 10 times the amount of any acid or any base you had. Okay, you want almost 10 times the amount of your base or your buffer properties present, the weak acid and the conjugate base. You want 10 times the amount of those things compared to any acid or base that you add to the solution, right? Questions on these? All right. So let's talking about number 3, property number 3. Here's a good problem. I actually have a poll for this question, so we'll answer it in a poll. You want to prepare a buffer solution with a pH of 5. Which acid and its conjugate base should you use? You have 4 different options down here: formic acid, acetic acid, propanoic acid, ascorbic acid, and the Ka values for each of these are listed. Okay, remember Ka is unitless. Any K value has no units, so don't worry about units here. How could I figure out which one to use? Remember, we want the one that's going to give us pH and pKa to be equal. So how could we figure that out? What do we need to do to answer this? You're going to, don't shout your answer out. You're going to answer it on a poll question. What should you do to figure out which acid and its conjugate base would be the best option for a buffer with a pH of 5? What should you do? I'm not going to tell you the answer. I want you to think based on what we talked about. What is pKa? How do you calculate pKa? How could you compare this? Put your answer in, and then we'll look at this. Okay, I know I'm kind of leaving you in the dark. You need to examine all your options. You need to calculate something here for every one of these before you just pick your answer on the poll. I'll give you probably just another 45 seconds or so. We're only about halfway voted. Anybody else want to vote? Okay, they're coming in. All right. I don't know if we're going to get any more votes. You've been going for almost 2 minutes, but still have 7 people who haven't voted. That's okay. I'm going to end the poll because we got to move on. So here's what you guys voted. Most people said acetic acid. So how do we even go about this? Well, you need to calculate the pKa for each of these and see which one's closest to 5. So you need to do the negative log of each of these. What did y'all get for the negative log of formic acid? Anybody? Negative log of formic acid. Whoa, what did that come out to be? Jenna said 3.7. What was the pKa for acetic acid? Again, we're just doing the negative log. If you didn't know how to go about this, negative log of each of these K values. So 4.7, that's closer for acetic acid. So definitely not going to be formic acid because 4.7 is closer to, we're seeing which one is closest to 5. That's the one we need to choose. Okay, what about propanoic acid? Negative log of 1.3 times 10 to the minus 5. You should have got, Kathleen said 4.8. And then lastly, for ascorbic acid, negative log of 7.9 times 10 to the minus 5. And it says 4.1. Okay, so now you just look at these and say which of these numbers is closest to 5, and that is propanoic acid. So that would be the weak acid and conjugate base system you'd want to choose to do a buffer here. Questions on that? So this is a great example. This is a great option for a multiple choice question on the exam. All right. Buffers, we have arrived at a buffer problem. I'm going to stop sharing these rules. So most people said acetic acid, but it should have been propanoic acid on the poll. All right, we've arrived at a buffer problem. How do we do a buffer problem? You are about to learn. So here's our Henderson-Hausbach equation. We're going to put this to use. And again, here's a generalized example of a weak acid conjugate base buffer equilibrium. Here is the way I will pose buffer questions. I mean, I'm just telling you right off the bat. You'll see one of these on the exam. What is the pH of a buffer solution made with 0.1 molar HF and 0.12 molar NaF? These are buffer components. Now, I have not told you which one's the weak acid and which one's the conjugate base, but I bet you could figure it out. Well, this is a dead giveaway. The Ka of HF, we don't have Ka values for conjugate base. The Ka values belong to the weak acid. So this right here is the weak acid. NaF, which is essentially going to break up into Na plus and F minus. Well, it's this F minus portion that's the conjugate base, right? Because it's HF minus the hydrogen ion. So we want to calculate pH. Well, here's our equation. All we do is plug stuff in. So pH, first though, we have to do one thing before we just plug stuff in. If we just plug this value in, is that correct? To just take 3.5 times 10 to the minus 4 and plug it into our equation? This is Ka. And in our equation, we have to plug in pKa. So the first thing we need to do, step number 1, is convert Ka to pKa. And we just did that like 5 times on the previous slide. So we'll just do the negative log of the Ka value. So 3.5 times 10 to the minus 4. That equals pKa. Jenna got 3.46 for the pKa. All right, now we're ready to plug in. We're literally just going to take these concentrations. The one thing we got to make sure is that we plug them in, the right one on top and the correct one on bottom. So we have pH equals pKa, which is 3.46. This is the value that you plug in, not Ka. I promise on the exam, people are going to plug in Ka instead of pKa. But I tried to warn you. Plus the log of, okay, now what goes on top? What goes on bottom? Well, look up here. What is A minus? A minus is the representative for the conjugate base. So we need to go find the concentration of the conjugate base and put that on top. And we said NaF, sodium fluoride, is the conjugate base. So we're going to plug in 0.12 molar. 0.12 molar on top. HA, in this case, is HF. So that is a key component of getting this whole thing right, is correctly identifying what the weak acid in the conjugate base is. And that concentration is 0.1 molar. And that's it. Now we just calculate pH. You do 3.46 plus the log of 0.12 divided by 0.1 and close your parentheses. When I did that, I got that pH of this buffer system starting out before we add anything is 3.54. Is that what y'all got? Okay. So we're 1/3 of the way done. That's 1/3 of the buffer problem. All right. Now we're going to look at this from two angles. What happens to pH? We're going to calculate pH when we add a base and when we add an acid. I forget which one's first. The base is first. Okay. Let's read this problem. What is the pH of? We have 1 liter of the buffer from above, 0.1 molar HF, 0.12 molar sodium fluoride. Same buffer as above. And I will never change the buffer on you. The buffer will be the same through all 3 parts of the buffer problem. When I add 0.02 moles of NaOH, what's going to happen to pH? We have 1 liter of our buffer when we add 0.02 moles of NaOH. Now, don't know. Oh gosh, I just swallowed a piece of ice. I'm okay. What happened? The first thing you might have noticed is that I give you your base in units of moles. But look over here, we have concentration of the buffer components in molarity. So these are apples and oranges. We have to make sure they're all apples or they're all oranges before we can do the problem. So we need to convert moles of NaOH to molarity. How do we do that? What is molarity? Molarity, remember from chapter 9, is moles of your solute per liter of solution. Well, we have those 2 pieces. Here's the liters of solution. Here's the moles of solute. So the first thing you always do here is you calculate the acid or the base, whichever component we're talking about. Here in this problem, it's the base. You calculate the molarity of it. All right. Now, I could tell you that you have 800 milliliters or 500 milliliters, or I could tell you have 1.2 liters, okay? But whatever the volume is, make sure it's in liters and calculate molarity. That's step number 1. So the molarity of NaOH here is that we're going to do 0.02 moles divided by 1 liter. And guess what? I made the math easy. The molarity is 0.02 molar. Now we're ready to go. I'm going to introduce something called an ice chart. Anybody heard of an ice chart before? We are going to look at, to plug in how the pH changes. Remember, when we add NaOH, what is our buffer going to do? Which component of either HF, this is the weak acid, or the conjugate base, is going to neutralize OH minus? Do you guys remember from that diagram we drew? Jenna says it's the weak acid, and she's correct. So if we have our little diagram, HF equilibrium with F minus, which is from the sodium fluoride here, and we add some OH from our base, sodium hydroxide over here, the HF is going to give up its hydrogen, and we're going to make water and then we'll inherently have more F minus. So it's the weak acid that's going to act to neutralize the base. So what happens to the concentration of HF? Is it going to go up or down? Jenna says down. We're going to use it up. We're going to donate some of it. We're going to lose some of it. So the concentration of this, after it neutralizes all the base, is going to go down. And that new concentration is what we'll plug in to our Henderson-Hasselbalch equation. But we have to calculate the new concentration. We'll do that in a second. What's going to happen to the concentration of our conjugate base? Well, we're going to make more of it inherently when we donate those hydrogens. So it's going to go up. So the way you keep this straight in your mind is if we add base, we add base. This is the conjugate base. If we add base, we're going to increase the concentration of the conjugate base, because on the ice chart, you're going to have to remember which column to subtract from and which column to add from. Let me show you what I mean. I bet I can do my ice chart down here. So step number 2 in a buffer problem is you make an ice chart. What an ice chart is we are going to look at the initial, the change, and the new equilibrium concentrations. I stands for initial, C stands for how they change, E stands for the new equilibrium concentrations of our weak acid and conjugate base. So I'm going to write the weak acid, here it's HF, and conjugate base is F minus. Initially, how much do we have? Those are given to us in the problem. So we're going to come plug in our initial concentrations. 0.1 molar, not moles, not percent, molarity. That's the units here, 0.12 molar. How are they going to change? Well, they're going to change by the amount of acid or base we add. They're going to change by this amount. We added 0.02 molar NaOH. Now, we need to know, do we subtract from the weak acid column or do we add to it? Well, we actually determine that over here with these little arrows. If we're going to decrease the amount of HF we have, we're going to subtract off 0.02 molar of that. We're going to lose 0.02 molar of our weak acid. That's how much is going to be used up to neutralize the NaOH. We're going to add to this column. We're going to make more of our conjugate base by the same amount. These numbers in the change column will always be the same. All right. One way people kind of confuse these is they get the signs, the plus and the minus mixed up here. But if you can remember, when you add base, you add base. When you add acid, you add to the conjugate acid side. All right, what's our new equilibrium? Well, now we just do the math. 0.1 plus 0.02 is 0.12. That's our new equilibrium concentration for the weak acid. 0.12, or sorry, I did that wrong. I didn't subtract. It should be 0.08. And on the conjugate base side, the F minus column, 0.12 plus 0.02 is 0.14. And these are the new equilibrium concentrations for H, F, and F minus. Now we just go plug those in to the Henderson-Hasselbalch equation, because the question is, what is the pH? So we'll do pH equals pKa. pKa has not changed here, so we're just going to go grab it from the previous slide, 3.4. 6 plus the log of, remember the concentration of F minus is going to go on top because it's the conjugate base, so we're going to do 0.14 divided by the concentration of our weak acid, 0.08. These are our new equilibrium concentrations we're plugging in. You always take the values from column or row E and we plug those into the Henderson-Hasselbalch equation, HH. So what's our new pH? .7. Now, again, earlier, I'm gonna let y'all finish writing for a second. Earlier, I mentioned that when you add, a base, a strong base or strong acid to a buffer, The whole point of the buffer is to resist any change in pH. And look, pH did change here, but not by much. Okay, it's still right around 3.5. Okay, so that's an okay change. It did fluctuate a little bit. So don't tell me that it doesn't change at all. It's going to fluctuate a little bit, but you see the buffer did a pretty good job keeping pH around what it was initially. Okay, so we're 2/3 of the way done. These are long problems, by the way. I don't know if I mentioned that. So they're going to be worth a lot of points on the exam. Now we're going to look at what happens if you add an acid. We have nitric acid here. It's a strong acid. Same idea. We're going to add 0.02 moles. I love to change these numbers, so don't get comfortable thinking you can just pull the same numbers down from the previous problem. Sometimes I'll say you had 0.5 moles or sorry, 0.05 moles, or now we have 800 milliliters of the buffer instead of 1 liter. But whatever numbers I give you, you calculate it all the same way. So the first thing is we're going to calculate the molarity, step 1, of HNO3, which is going to be 0.02 moles of HNO3 divided by 1 liter. So our molarity is the same, 0.02 molar. So that's how much acid we are going to add. Now we're going to make our ice chart. Go ahead and write out your rows ICE. Same buffer, so we still have good old H minus or HF and good old F minus. And we still have the same initial concentrations. 0.1 molar here, 0.12 molar there. None of that changes. The rest of this will be different. So remember, if we have our buffer diagram, if we add some acid, H plus is going to be created. This right here, HNO3, is going to dissociate into H plus and NO3 minus. So it's this H plus here that is threatening to change pH. So how will the buffer respond? We're going to throw our defensive team in, swoop up, snatch up, whatever you want to say, the H plus, and create more of our weak acid. So we need to know what signs to plug in for our C column, our C row. Which side is increasing and which side is decreasing? Well, we're using up our conjugate base this time. So the concentration of it will go down and the concentration of weak acid will go up. So that right there tells you which side to put the plus sign on and which side to do the minus. Remember, if you add base to the buffer, you increase, you add on the base column. If you add acid here, we're going to put a plus sign, add to the weak acid column. So plus and minus. By how much? 0.02. And then you calculate your new equilibrium concentrations. For HF, it is 0.1 plus 0.02 this time. For F minus, it's 0.12 minus, so 0.10. And these are what we go plug in to Henderson-Hasselbalch equation to solve for pH. So pH, I'm just grabbing this equation right here. We're just plugging in pH equals, what was our pKa? Has not changed, 3.46. It's what we calculated in the first step. And it's going to be plus the log. Make sure you get the top and bottom right here. Conjugate base, F minus, so that's 0.1 goes on top. And the weak acid goes on bottom, 0.12. So now what's pH? Abby got 3.38, Jenna got 3.38. So you see pH went down a little bit, but that makes sense because we're adding something that's acidic. So it's going to move it a touch towards the more acidic pH range. But overall, it's pretty close to where it was. It didn't change by much. All right, woo, that was a big problem. Okay, so that'll be worth a decent amount of points. Something like this. I won't give you the same weak acid conjugate base system. but a three-part problem like this on the exam, okay? And we'll do another one on review day, the day before the exam. So I really hope you can join us. All right, let's look at buffers in the body. We've got about 14 minutes left. So we're gonna finish these slides up. We may or may not get to the titration slides, but we've talked about titrations already from lab this week. So hopefully y'all are okay with that. Buffers in important systems, buffers in the body, really. Proteins are a buffer, okay? They can act as acids or bases, depending on the protein. We're not going to get into that. I just wanted you to be aware. I mean, you have over close to 60,000 proteins in your body. So we have tons and tons of different little protein buffer systems. In your cells, you have a phosphate buffer system, okay? And that looks like this. This one is the weak acid. And this one's the conjugate base. All right, and that maintains the pH it needs inside cells. And then this one is the one we're going to spend the rest of the day talking about, bicarbonate buffer. This is your blood buffer system. Okay, so carbonic acid, this is the weak acid, will donate a hydrogen and it will leave you with bicarb. Remember from week 1 of class, your polyatomic chart? One of those polyatomic ions was bicarbonate, bicarb. Also known as hydrogen carbonate, but bicarb. All right, you also have to know that carbonic acid is a really unstable acid, and it can break down a different way. Instead of just disassociating with one hydrogen, it can also break down to give you water and carbon dioxide. It can break down 2 different ways. It can disassociate and give away a hydrogen ion, or it can break down into carbon dioxide and water. All right. And so here's what gets crazy. There's 2 equilibrium systems in one reaction. Okay. And equilibrium here is crucial to maintain physiological pH. And I think we said it in a lecture before, but what is physiological pH? What do we need to keep our blood pH around?
7.4.
Mm-hmm. It's usually a range that it hangs out between 7.35 to 7.45, with 7.4 being in the dead middle of that. So let's talk about how our body actually responds to keep that pH. You can respond with breathing, and your kidneys are another major player here. So changes, the first one is that changes in respiration can influence blood pH. You can have 2 different conditions: respiratory alkalosis, meaning a basic blood pH a little bit too high, or respiratory acidosis, blood pH is a little bit too low. And those can both be corrected by equilibrium shift, so a shift in equilibrium, whoops. And it can also be helped from kidney function. Okay, all of these play a role in keeping pH where it is. And we're going to walk through examples like what happens if we hyperventilate or hypoventilate. How does that affect blood pH in just a minute? All right, changes in kidney, well, kidney function, okay, as well, also influence pH, blood pH. It's very sad, but people experience kidney failure. I have a dear family member who is about a 3 out of 5 in kidney failure right now, and so that's not good. You need at least one of your kidneys, right? And so kidney failure usually means your blood pH is going to drop some, and that can be corrected by, again, a shift. This is all going to be shifts in equilibrium, and then changes in respiration. So you guys remember our old friend Le Chatelier? Don't forget him, because that's how this whole thing works. Understanding how equilibrium is going to shift is all Le Chatelier's principle. This is another reason I think chapter 10 is so hard, because it is built on a lot of key properties: equilibrium and Le Chatelier's principle, all things from chapter 7. Other things, external factors also influence blood pH: metabolism, Okay. And then different things that we eat, different medications that we take can all change blood pH. So our body is constantly working to fight and keep it where it needs to be. We're going to walk through these, let's see, next two slides. And if we get through those are the main things I want to get through. If we don't cover anything else after that, it won't be on the exam. But let's try to get through these 4 scenarios before time is up. Okay, what happens to blood pH if you hyperventilate? So look at this right here. Are you increasing or decreasing respiration when you hyperventilate? You're increasing, you're breathing really fast, okay? So if we're increasing respiration, what's happening to the levels of CO2 in our body? If we're breathing and exhaling really quickly, what's happening to the amount of CO2 in our body? Is it increasing or decreasing? Lower. Okay, so we're going to drop the concentration of CO2. If you're zoned out, I really need you to zone in these next couple minutes because this stuff is going to be on the exam too. All right, so we're going to lower the amount of CO2. So what happens to equilibrium right here? If we're just looking at this setup, which way does equilibrium shift when we take some CO2 away? Yeah, it's going to shift towards the reactants, okay? Equilibrium will shift this way. And it will shift this way across the whole span of the reaction. So if equilibrium, let's see, first off, we're going to lower, I'm going to write this down here, lower CO2. And then what that's going to create is equilibrium is going to shift left to replace the CO2 that we are losing because we're breathing so fast. Now, if equilibrium shifts left, let's look over here. What's going to happen to the concentration of our products, specifically H plus being the thing that affects pH? What's going to happen to the concentration of H plus? Will it go up or down? If equilibrium shifts this way, it will go down. Yep, we're going to lose H plus. Now remember, we said if H plus goes up, that pH goes down. So guess what? If concentration of H plus goes down, pH rises. And so the question is, what happens to your blood pH? Well, pH is going to go up. pH is going to increase. Okay. This is what I want you to be. It's kind of like a code. I feel like we're writing our own code language here. But this is the kind of code I want you to write if I pose questions to you like this on the exam, okay? All right, now let's examine it from the flip side. What happens if we hypoventilate? Sometimes, anybody prone to fainting? I can be. Needles, I always warn people who draw my blood, I might pass out. It's not something I can really control. It might happen. That's why I was never meant to be a nurse or a doctor or anything. Okay, but if we hypoventilate, our breathing slows down, so we're decreasing respiration. And the very opposite thing is happening to CO2. Now we're going to build CO2 up in our body. We're going to increase the concentration of CO2 in our body. So that's the first thing we're going to write down. If we slow down our breathing, CO2 will have a buildup of CO2 in our body. Okay, now what's going to happen to equilibrium? According to Le Chatelier's principle, if we increase CO2, equilibrium will shift to the right. Yep, it will shift this way to use up some of that and restore equilibrium. So we are going to, equilibrium will shift right. What's that going to do to our products? Bicarbonate H plus. We're going to make more of them. So we're going to increase the concentration of H plus. And I'm serious, you really need to at least somewhat have these memorized or written down somewhere, these little relationships. They're going to help you on this problem. Increase in H plus means a decrease in blood pH, lowers blood pH. Is this what happens to people with sleep apnea? I'm not very well versed in sleep apnea. Anybody have a comment on that? Somebody remind me, I sleep like a rock unless I have a crying baby. Okay. I guess I don't sleep as deeply as I used to. Is that having trouble falling asleep, or, oh, it's when you stop breathing when you're sleeping? Yeah, that's scary. Maybe it is that your breathing just slows down to the point that your blood pH, it could be something else that causes your blood pH to shift, which would result in slower breathing. So the slower breathing has got to be a result of something that's happening in your blood pH. And we're actually about to look at it from the kidney standpoint. And I wonder if it is related to kidney function at all. That would be an interesting question. So let's look at this. What happens to your breathing? I didn't answer your question, Savannah, because the answer is I'm actually not sure, but it's something I might look into. What happens to your breathing rate if your kidneys can no longer store bicarb? So if you have kidney failure, and that's what kidneys do. They pull bicarb out, or they dump it into the blood when we need it. So if we can't store it, meaning we need to store it. That's what our body's needing us to do. It's just that our kidneys can't. So what's going to happen to the amount of bicarb if we cannot pull it out of the blood and store it in the kidneys? What will happen to the concentration of bicarb, HCO3 minus, in our blood? It will increase. We need to store it. We need to pull it out of the blood, but our kidneys aren't functioning properly, so we can't. What's going to happen to equilibrium if we have a buildup of this right here, bicarb? Equilibrium will shift to the left. And then what's going to happen to the levels of CO2 in our body? If we shift left to use up some of the bicarb because our kidneys can't, yep, it will increase. And what happens to breathing? Will we need to breathe faster or slow our breathing down? We need to get rid of CO2. We have too much of it in the body now. So if we need to get rid of it, we need to exhale faster. So we need to hyperventilate. Yep. Okay, here's a random question. No, I guarantee you no one else will ask you this today. But I'm going to ask you, what happens to your breathing rate if you accidentally inject yourself with NaOH? Okay, don't do that, number one. But if you did, just to see, what would happen? This is kind of a out of the box question. This actually doesn't necessarily start with the kidneys or your breathing. I want you to look at this equation and say, what component in this whole equation, CO2, water, H2CO3, bicarb, or H+, would react with NaOH? One of those items should jump out at you. What item in this whole equation would react with NaOH? Jenna says HCO3 minus. Jenna, think about that. There's a negative charge on bicarb, and NaOH is also negatively charged. It should be the H+, okay? H+ right here is, I mean, like magnetic. It's really attracted to OH minus, okay? So this H+, if we inject ourselves and we have some Na and some OH minus over here in our blood, these two things are absolutely going to react with one another, okay? So if we inject ourselves with NaOH, what's going to happen to the concentration of H+ in our blood? If it is going to zoom over to OH minus and bind up with it to be neutralized, make water, we're going to lose it in our blood. Decrease the amount of that. All right, and the question is here, what's going to happen to our breathing rate? Not what happens to pH, but what happens to our breathing rate? Well, if we're losing H+, our blood pH is suddenly increasing, and our body doesn't want our blood pH to increase. So we can shift equilibrium this way to the right. To replace the H+ that this sodium hydroxide is using up. And if equilibrium shifts right, the concentration of CO2, what's going to happen to that? We're going to lose it. We're going to decrease the amount of CO2 in our blood. And to fix that, our body will slow down our breathing. So we'll hypo. If we can slow down our breathing, we can increase the amount of, we're not exhaling CO2 as fast. So we'll restore the needed levels of CO2 in our body so that equilibrium is maintained. And overall, no shift in blood pH occurs. All right, we are at time. The rest of this was just talking about titrations. So I won't put that directly on the